This is the open ocean, where water itself becomes a weapon, a force that doesn't explode, doesn't burn, but pulls everything down, a whirlpool powerful enough to drag steel into its center. No warning systems, no escape routes. If a warship gets caught, it fights the ocean itself, and the ocean doesn't lose. Section 1. Introduction. The ocean is often imagined as an open, empty expanse, vast, silent, and predictable to those equipped with modern technology. But beneath that surface lies a system of immense, constantly shifting forces. Invisible currents collide. Pressure gradients shift without warning. And in certain regions, the sea begins to rotate. Not as waves, not as storms, but as something far more controlled and far more dangerous. Whirlpools are not myths. They are real, measurable phenomena, born from the interaction of tidal forces, geography, and fluid dynamics. In most cases, they are brief and localized. But in specific parts of the world, they grow into powerful, recurring systems capable of destabilizing vessels, overwhelming navigation, and dragging objects downward with relentless force. For centuries, sailors described these formations as gateways to the unknown, spinning voids in the ocean that could swallow ships whole. Many of those accounts were exaggerated. Fear, isolation, and limited understanding turned natural phenomena into legends, but the danger itself was never fictional. Today, we understand whirlpools not as supernatural anomalies, but as extreme hydrodynamic events. They form when massive volumes of water are forced through narrow channels, accelerating and colliding with opposing currents. The result is rotational energy, a vortex, capable of generating violent turbulence both on the surface and below. And while smaller vessels are the most obvious victims, the question remains: what happens when something far larger enters this environment? A modern naval destroyer is a product of precision engineering. Built for combat, designed to withstand explosions, storms, and sustained operations in hostile conditions. It carries advanced propulsion systems, reinforced hull structures, and sophisticated navigation controls. But none of those systems were designed to fight a rotating ocean. Because a whirlpool doesn't attack like a wave. It doesn't strike and pass. It traps. It destabilizes. It removes control. And in that moment, control is everything. This documentary examines the reality behind one of the ocean's most misunderstood threats. Not through fiction or simulation alone, but through real-world environments, historical encounters, and documented disasters. Because the true question isn't whether whirlpools exist. It's whether anything, even a warship, can survive when the ocean begins to turn against it. Section 2. Geography and physical carvings. Whirlpools do not appear randomly. They are not scattered across the ocean without pattern. They form in specific places, where geography forces the ocean into conflict with itself. These locations share one defining characteristic: constriction. Narrow straits, sharp seabed drops, channels where enormous volumes of water are forced through limited space, twice a day. As tides rise and fall under the gravitational pull of the moon and the sun, billions of tons of seawater begin to move. In open ocean, this movement is gradual, almost unnoticeable. But when that same water is funneled between islands or through tight passages, its speed increases dramatically. And when speed increases, stability disappears. Saltstraumen. Norway, just north of the Arctic Circle, lies Saltstraumen, one of the most powerful tidal currents on Earth. Here, nearly 400 million cubic meters of water are forced through a narrow strait every 6 hours. The channel is just over 150 meters wide in places. As the tide shifts, water accelerates to speeds exceeding 40 kilometers per hour. The result is a chaotic surface of spinning vortices, some reaching up to 10 meters in diameter. To a distant observer, it may look like turbulence, but inside the current, the water behaves unpredictably. Rotational forces pull in multiple directions. Eddies collide. Small whirlpools merge into larger ones. For small vessels, this is already a high-risk environment. For larger ships, the danger is different. Not immediate destruction, but loss of control. Moskstraumen. Norway, say further west, off the coast of the Lofoten Islands, lies the Moskstraumen, one of the most infamous whirlpool systems in maritime history. This is not a single vortex, but a vast field of interacting currents, driven by the collision of tidal flow with complex seabed topography. The ocean floor here rises sharply, forcing deep water upward while surface currents move laterally. The result is instability across multiple layers of the water column. Sailors navigating this region for centuries reported violent spinning waters, sudden shifts in direction, and vessels struggling to maintain heading. While modern measurements show that the Moskstraumen is unlikely to large ship's hull, its power lies in something more subtle. It disrupts navigation. And in confined waters, even a brief loss of control can escalate into disaster. Korivrekan, Skålen between the islands of Jura and Skarba, the Korivrekan whirlpool forms over a deep underwater pinnacle, a column of rock rising sharply from the seabed. As tidal currents rush over this obstruction, water is forced upward and outward, creating one of the largest permanent whirlpools in the world. At peak flow, standing waves can reach heights of over 9 meters, and the vortex below generates intense downward suction. This is not just surface turbulence. It is vertical movement, water being pulled down as well as spun around. Reports from the area describe roaring sounds, violent churning, and sudden drops in water level around the vortex. For any vessel caught too close, stability becomes unpredictable. Naruto strited, Japan in the Naruto Strait. Powerful tidal exchanges between the Seto Inland Seas and the Pacific Ocean create rapidly forming whirlpools that can appear and disappear within minutes. Here, timing is everything. Currents can reach speeds of 20 kilometers per hour, and whirlpools form in clusters, multiple rotating systems interacting simultaneously. Unlike larger, more stable whirlpools, these are dynamic and short-lived. But their unpredictability makes them especially dangerous. A vessel entering calm water can suddenly find itself surrounded by rotating currents with no clear escape path. The common factor, despite their differences, all of these locations share the same underlying conditions. Massive tidal movement, constrained geography, uneven seabed structures opposing or intersecting. Currents, these elements combine to create rotational instability, the foundation of whirlpool formation. But perhaps the most important detail is this. None of these environments are large enough to destroy a modern warship through sheer suction alone. That idea of a ship being pulled straight down into a vortex is largely a myth. The real danger is more complex, because a whirlpool doesn't need to sink a ship directly to destroy it. It only needs to take away control. Section 3. Environmental Systems. To understand how a whirlpool becomes dangerous, especially to something as large as a naval destroyer, you have to look beyond the surface. Because what appears as a spinning circle of water is actually the visible edge of a much larger system in motion. Tidal forces, the engine behind the motion. At the core of every major whirlpool is a predictable, unstoppable force, the tide. Driven primarily by the gravitational pull of the moon, tides move vast volumes of ocean water across the planet in repeating cycles. In open water, this movement is slow and distributed. But in constrained regions, straits, channels, and coastal inlets, it becomes concentrated. Twice a day, water surges in. Twice a day, it rushes back out. And when opposing tidal flows meet, they don't cancel each other out. They collide. Cranction interaction, where instability begins. When two currents moving in different directions intersect, the water begins to shear, layers sliding past one another at different speeds and angles. This creates turbulence, but in certain conditions, turbulence evolves into rotation. Instead of chaotic movement, the energy begins to organize itself into a circular pattern, a vortex. Once that rotation begins, it feeds itself. Faster flow strengthens the spin. Stronger spin pulls in more water. More water increases the energy of the system. This is how a whirlpool forms, not as a hole in the ocean, but as a rotating mass of water with a defined center and outward force gradients. Vortex Pacisiacs. What's really happening? At the center of a whirlpool, pressure drops slightly compared to the surrounding water. This creates a downward pull. Not strong enough to instantly drag large ships under, but significant enough to affect buoyancy and stability. Around that center, water accelerates in a circular path. The outer edges move slower. The inner regions move faster. This difference in velocity creates angular momentum, a force that resists disruption. Once established, the vortex becomes a stable system, difficult to break apart from the outside. For a vessel entering this environment, the problem is not being pulled straight down. It's being subjected to multiple forces at once. Rotational drag, pulling the hull sideways. Vertical currents affecting buoyancy. Turbulence disrupting propulsion efficiency. A ship is designed to move forward. A whirlpool forces it to move in every direction at once. Kyle vs. Perception. Popular imagination often exaggerates whirlpools as massive ship-devouring funnels, capable of swallowing entire vessels instantly. In reality, most whirlpools are smaller in scale. Even the largest known tidal vortices rarely exceed a few tens of meters in diameter, but size is misleading, because the destructive potential of a whirlpool is not defined by how wide it is, but by how unstable the surrounding water becomes. A large warship may not be pulled under in a single motion, but it can be forced off course, rotated broadside to the current, unable to maintain propulsion alignment, and in that state, it becomes vulnerable. Hydrodynamic stress on the vessels. A modern destroyer relies on controlled interaction with water. Propellers generate thrust by pushing water backward, rudders steer by redirecting flow stabilizers. Maintain balance against waves, but in a whirlpool, water is no longer moving in a predictable direction. It's spinning, rising, and falling simultaneously. This disrupts every system the ship depends on. Propellers lose efficiency as water flow becomes inconsistent. Rudders struggle to maintain directional control. The hull experiences uneven pressure from multiple angles. And perhaps most critically, the ship can begin to yaw, rotating uncontrollably around its vertical axis. Once that happens, regaining control becomes extremely difficult. The critical threshold, there is a point, not defined by size but by conditions, where a vessel transitions from controlled navigation to passive drift. This is the threshold every ship must avoid, because beyond it, the ocean is no longer something to move through. It becomes something you are trapped inside, and a whirlpool is one of the fastest ways to reach that point. Long before the physics was understood, the ocean was interpreted through fear. Sailors navigating the northern seas of Europe encountered something they could not explain. Areas where the water moved against itself, where ships lost steering without warning, and where the sea appeared to rotate as if pulled by an unseen force. They called them maelstroms. Viking navigation. First encounters. As early as the Viking Age, Norse seafarers traveling along the Norwegian coast were forced to navigate through some of the most dangerous tidal systems in the world, including what is now known as the Moskstraumen. These sailors were highly skilled. Their ships were built for flexibility, capable of handling rough seas and coastal maneuvering. But even they treated certain waters with caution. Timing was everything. They learned to pass through narrow straits only during slack tide, the brief period when water movement slows before reversing direction. Entering too early or too late meant facing accelerating currents that could overpower steering. There were no instruments, no charts of current velocity, only observation and experience. And even then, mistakes happened. Early European accounts, by the 16th and 17th centuries, European explorers and traders began documenting these phenomena in written records. Descriptions of the Moskstraumen spoke of water spinning like a mill wheel, ships being dragged off course, objects disappearing into the center of rotating currents. But without scientific understanding, these accounts became exaggerated over time. Stories evolved into warnings. Warnings turned into legends. Some claimed entire ships vanished without a trace. Others described whirlpools so large they exposed the ocean floor at their center. These details were not accurate, but they reflected something real. A loss of control that felt absolute. The role of literature, my vs. reality. In 1841, writer Edgar Allan Poe published A Descent into the Maelstrom, a fictional story inspired by the Norwegian whirlpools. In it, a massive vortex pulls ships downward into a spiraling abyss. The story captured the imagination of readers worldwide and reinforced the idea of whirlpools as unstoppable, ship-destroying forces. But Poe's version, while powerful, was not reality. No known whirlpool on Earth is capable of swallowing a large ship whole in the way described. Yet the fear persisted because while the scale was exaggerated, the danger was not. Transition to science. By the 18th and 19th centuries, advancements in navigation and oceanography began to replace myth with measurement. Sailors started recording tidal timing, current speeds, geographic patterns. Scientists studied how water behaved when forced through narrow channels and over uneven seabeds. The whirlpool was no longer seen as a supernatural force, but as a predictable outcome of physical conditions, a system. One that could be understood, but not controlled. Lessons from early navigators. What early sailors lacked in technology, they compensated for with discipline. They respected the limits of their vessels. They avoided known danger zones during peak flow. They adapted their routes to the behavior of the sea. And most importantly, they understood that survival depended not on strength, but on timing and awareness. The enduring reality modern ships are stronger, faster, far more advanced. But the environments those early sailors feared still exist, the same currents, the same narrow straits, the same rotating forces beneath the surface. Only now, the question has changed. It's no longer about wooden ships and sail. It's about steel hulls, powered propulsion, and whether modern engineering can overcome forces that were once only avoided. Section 5. Real instances disasters. Whirlpools rarely destroy ships in a single dramatic moment. There is no sudden drop into an abyss. Instead, the danger unfolds differently. Control is lost first, then stability, and only after that, survival becomes uncertain. Across history, multiple real-world incidents reveal how vessels, from small fishing boats to advanced naval ships, are overwhelmed not by a single force, but by a combination of currents, rotation, and human limitation. Moskstraumen, centuries of near misses. For hundreds of years, the waters off the Lofoten Islands have challenged even experienced sailors. The Moskstraumen is not one whirlpool, but a constantly shifting system of rotating currents. Ships entering at the wrong time have reported sudden lateral drift, loss of rudder effectiveness, inability to maintain heading. Historical logs from Nordic and later European vessels describe ships being spun partially off course, forcing crews to reduce sail or risk capsizing. No large warship was ever swallowed here, but that was never the real threat. The danger was being pushed off trajectory, toward rocks, shallow waters, or collision paths with other currents. In confined seas, that's enough. Corryvreckan, the Scottish maelstrom. The Corryvreckan whirlpool, located between the islands of Jura and Skarba, has a long history of maritime incidents. Fishing boats and small vessels have repeatedly been caught in its rotating currents, especially during peak tidal exchange. In documented cases, boats were capsized within minutes. Engines failed to compensate for rotational drag. Crews were thrown overboard due to violent turbulence. One of the most notable historical encounters involved author George Orwell in 1947, who navigated near the Whirlpool while boating in the area. His vessel lost control in the turbulent waters and nearly capsized, an incident that could have easily turned fatal. The Corryvreckan does not destroy through suction. It destabilizes rapidly and unpredictably. Naruto Strait. Precession or consequence. In Japan's Naruto Strait, whirlpools form and dissipate within minutes, driven by fast-moving tidal exchanges. While modern navigation has reduced major disasters, smaller vessels still face significant risk. Documented incidents include fishing boats being pulled into rotating current zones, engines overwhelmed by shifting flow direction, sudden loss of steering due to multi-directional forces. The key danger here is unpredictability. A vessel can enter calm water and within minutes find itself surrounded by multiple vortices forming simultaneously. There is no stable direction, no clear exit, only reaction time. Saltstraumen. Power without warning. Saltstraumen's current is one of the strongest on Earth, and while it is well charted, accidents still occur, particularly with smaller craft. Local reports and maritime records describe boats being dragged into high-speed current channels, collisions caused by sudden lateral movement, loss of propulsion effectiveness due to turbulent inflow. Even experienced operators can misjudge timing, and once inside the fastest part of the current, turning back is no longer an option. The vessel moves with the water, not against it. Typhoon Cobra. The limits of warships. December 1944. The Philippine Sea. The U.S. Navy's Third Fleet encountered Typhoon Cobra, one of the most destructive storms in naval history. While not a whirlpool, the event demonstrates what happens when large warships lose control in extreme ocean conditions. 3 destroyers, USS Hull, USS Monaghan, and USS Spence, were lost. These were not small vessels. They were fully operational warships. Yet under extreme forces, ships rolled beyond recovery angles. Ballast instability worsened the situation. Waves and currents disrupted propulsion and steering. The result, capsizing and sinking. The lesson is critical. Even without a vortex, chaotic water movement alone can destroy a destroyer. A whirlpool introduces a similar loss of control, but in a confined, rotational system. USS Enterprise, overpowered by the sea in 1945, the USS Enterprise CV-6, one of the largest aircraft carriers of its time, encountered a powerful typhoon. Despite its size and advanced design, the ship suffered severe structural strain and operational disruption. Aircraft were lost. Deck systems failed. Control became increasingly difficult. Again, no whirlpool was present. But the core issue was the same. When water stops behaving predictably, even the largest ships struggle to maintain stability. The pattern across all these incidents, one pattern emerges. Ships are not destroyed instantly, they are overwhelmed gradually. First, navigation fails. Then, control systems struggle. Finally, the vessel becomes vulnerable to capsizing, collision, or structural failure. A whirlpool accelerates this process. It combines lateral force, rotational motion, and vertical instability into a single environment. And once a vessel is caught in that system, escape becomes a matter of timing, power, and luck. Section 6. Modern naval encounters. Present-day risks. Modern naval destroyers represent the peak of maritime engineering. Ships like the Arleigh Burke class are designed for combat in hostile environments, capable of operating through storms, launching precision weapons, and sustaining damage while remaining operational. They are built to fight. But they are not built to fight the ocean itself. Design vs. reality. A modern destroyer relies on three core systems to maintain control. Propulsion, powerful gas turbine engines driving multi-ton propellers, steering, advanced rudder systems, and digital navigation control stability. Hull design optimized to cut through waves, not rotating currents in open water. These systems provide near-total command over movement. But in a whirlpool environment, the rules change. Because control depends on predictable water flow. And in a vortex, nothing is predictable. Propulsion limitations. A destroyer's propellers generate thrust by pushing water in a consistent direction. But inside a whirlpool, water flows sideways, not just backward. Rotational currents disrupt propeller intake. Cavitation risk increases as pressure fluctuates. The result is reduced thrust efficiency. Engines may operate at full power, but the ship doesn't respond as expected. It moves, but not where it's supposed to. Loss of steering control. Rudders function by redirecting water flow along the hull. In stable conditions, this allows precise directional control. But in rotating water, flow direction changes constantly. Rudder input becomes inconsistent. Steering commands lag or fail entirely. The ship begins to yaw, turning off course without command. Correcting this requires stable flow. A whirlpool removes that stability. Lateral forces. The hidden threat. Unlike waves, which impact a ship from predictable directions, whirlpools generate multi-directional forces. This creates sideways drag along the hull, uneven pressure distribution. Rolling motion combined with rotation. A destroyer is long and relatively narrow. If turned broadside to the current, it presents a large surface area. At that point, the water begins to control the ship, not the other way around. Modern naval patrols. Because of these risks, modern navies do not attempt to fight extreme hydrodynamic zones. They avoid them. Naval charts clearly mark high current straits, tidal hazard zones, known vortex-forming regions. Training emphasizes timing passage through narrow channels, maintaining safe distances from turbulent zones, avoiding peak tidal flow periods. NATO and U.S. Navy operational guidelines treat these areas as navigation hazards, not challenges to overcome. Real one encounters. While direct encounters between destroyers and major whirlpools are rare by design, modern ships do regularly face extreme ocean conditions that mirror similar risks. Case reports and naval records describe ships experiencing temporary loss of steering in strong cross currents, sudden yawing in confined waterways, difficulty maintaining heading during rapid tidal shifts. In each case, the response is the same: reduce speed, stabilize orientation, exit the area immediately, because prolonged exposure increases risk exponentially. Simulation vs. reality. Modern simulations can model whirlpool behavior and ship response. They show that large ships are unlikely to be instantly submerged. Structural integrity usually holds under short exposure, but controlled degradation happens rapidly. Within minutes, a vessel can transition from controlled navigation to partial drift. And once drift begins in a confined, rotating system, recovery becomes uncertain. The critical weakness. A destroyer's greatest strength is precision. Its greatest weakness is dependence on control. Remove that control, even temporarily, and the ship becomes vulnerable in ways its design cannot fully compensate for. A whirlpool does not need to break the ship. It only needs to confuse its movement, disrupt its balance, force it into a position where the ocean decides what happens next. Section 7. Final conclusions. For centuries, humans have built ships to conquer the sea. Stronger hulls, more powerful engines, advanced navigation systems capable of tracking every movement across the globe. And yet, The ocean has never been conquered, only navigated. Whirlpools are not the largest threat at sea. They are not the most violent. But they represent something more fundamental, a loss of control in an environment where control is everything. A modern destroyer can withstand explosions. It can survive missile impacts. It can operate in storms that would destroy smaller vessels. But it cannot change the physics of water. It cannot force stability into a system built on motion. Because the ocean does not fight like an enemy. It does not attack with intent. It simply follows its own rules: gravity, pressure, flow. And when those forces align in the wrong place, at the wrong time, even steel becomes secondary. The idea of a whirlpool dragging a warship into the depths is largely a myth. But the idea of that warship losing control, drifting, turning, unable to respond, that is real. And in the open ocean, reality is enough. There are no second chances out here, no safe boundaries, no guarantees, only a narrow margin between control and surrender. And when the water begins to turn, that margin disappears.